So this is the review for the Chapter 3 honors test. We're going to start by balancing and identifying types of equations. The first equation, methane gas reacts with oxygen gas to produce carbon dioxide gas and water vapor. So methane, which is CH4, gas reacts with oxygen, which is O2. You have to always remember oxygen's O2. And then we've got CO2 and water vapor, which is the gas state of water. So if we count up the elements on both sides, we've got a carbon, 4 hydrogens, and 2 oxygens on this side. And on the right we have 1 carbon, 2 hydrogens, and 3 oxygens, 2 in the carbon dioxide, 1 in the water. So if we look at the hydrogens, because the carbons are already okay, we look at the hydrogens. If I put a 2 in front of that hydrogen, it changes the number of hydrogens to 4. Changes the number of oxygens also to 4. Total, 2 here and 2 here now. So the only thing I need to change on the other side is by putting a 2 in front of the oxygen. That gives me 4 oxygens on both sides. Now we're balanced. The type of reaction, you have oxygen here as one of the reactants, so that indicates it's a combustion reaction. Combustion reactions can sometimes also be synthesis reaction, but in this case we have 2 products. Anytime there are 2 products, it's not a synthesis reaction. So it's combustion but not synthesis. Next reaction, we've got sodium chloride, which is NaCl, aqueous, means dissolved in water, so it's in a solution, plus sulfuric acid, H2SO4. And that is aqueous, and it's going to react with, those two are going to react to produce sodium sulfate, which is Na2SO4. That's aqueous. I'm running out of room though, so we're going to call it, and then hydrochloric acid is HCl. So again, divide up the sides. We've got sodium, we've got chlorine, we've got hydrogen, and since sulfate appears as a polyatomic ion on both sides, I'm going to keep that as a unit. We've got 1, 1, 2, and 1. On this side, I've got sodium, 2. I've got SO4, there's 1 on this side. I've got 1 chloride, and I've got 1 hydrogen. So the only one that's off here, or the 2 that are off, are the sodium and the hydrogen. So if I put a 2 in front of the sodium over here, that gives me 2 sodiums, also gives me 2 chlorides. And then to balance it, if I put a 2 in front of the HCl, the hydrochloric acid, it gives me 2 hydrogens and now 2 chlorides. So that's balanced. And the type of reaction here, we've got 2 compounds on the left, we've got 2 compounds on the right. The difference is that the chloride and the sulfate have changed places. Anytime you have 2 compounds that sort of have the 2 halves swap, that's called a double replacement reaction. Double replacement. So 2 compounds for reactants, 2 compounds per products, and these are typically ionic compounds and acids, so the 2 halves of each compound trade partners and you get 2 different compounds as the products. So silver sulfide. Sulfide is just sulfur. Sulfite would be SO3, but sulfide, IDE, is just plain sulfur. That's aqueous, but I'm going to leave out the symbol to save some space. Reacts with solid aluminum, and the result is solid silver plus aluminum sulfide, which is Al2S3. So let's count this up. We've got 2 silvers, 1 sulfur, and 1 aluminum. On this side we've got 1 silver, 2 aluminums, and 3 sulfurs. So I'm going to need to figure out the sulfide. Okay, if I put a 3 in front of the silver sulfide. That gives me 3 sulfurs, so that matches that up. It gives me 6 silvers, but that's okay. I'm going to come back and deal with that later. And in order to balance the aluminums, I need to put a 2 in front of this aluminum, which gives me 2 on both sides. And then finally I'm going to fix the silvers by putting a 6 there, which gives me 6 silvers on both sides. So 3, 2, 6, and 1 are the coefficients here. This type of reaction where we have a compound and an element on the reactant side, and then the 2 metals in this case trade places. So the silver now is by itself, the aluminum is part of the compound. That's called a single replacement. So double replacement is 2 compounds where the halves trade places. When you have 1 compound and an element where the elements trade places, that's called a single replacement reaction. Okay, so now we're just going to balance a few equations. Okay, in this one we have 1, 2 nitrogens here and here. Since the nitrate is not a polyatomic ion on the product side, on the right, I can't keep it as a unit, so I have to break up the nitrogen and the oxygen in that case for the counting. So the 2 nitrogens that are in the ammonium nitrate are counted individually, and then there's 4 hydrogens and 3 oxygens. On the right I've got 2 nitrogens, I've got 2 oxygens, actually 3 oxygens because I've got 1 in the H2O, and then I've got 2 hydrogens. So I'm going to have to change the hydrogen, but I also need to look at the fact that if I change this water to get more hydrogen, I'm going to have more oxygen. This is going to go to 4. Now I've unbalanced the oxygen. There's only 1 reactant, so I'm going to have to see what happens if I double that. I end up with 4 nitrogens, 8 hydrogens, 6 oxygens. Now let's come back and take a look at the other side and see what happens. If I put a 4 here, because that gives me 8 hydrogens, it also gives me now 4 oxygens plus 2, which is 6. Now that matches up. So the only thing that doesn't match is the nitrogen, and if I put a 2 in front of that nitrogen, it gives me 4, because nitrogen is N2 here. So 2, 2, 1, and 4 are the coefficients. This would be a decomposition reaction if we were classifying it. Alright, and the next one, this one's kind of tricky. So we've got carbon, there's 3 of those. I've got 5 hydrogens. And again, the nitrate does not appear on both sides, so I can't treat it as a unit, so I'm going to count them separately. There's 3 nitrogens because the little subscript outside the parentheses means there's 3 times as much stuff in the parentheses. So 9 oxygens. On the other side, I've got 1 carbon, I've got 2 hydrogens, I've got 2 nitrogens, and I've got 2, 4, 5 oxygens. Okay, so this is going to make it tricky because I've got odd numbers. It's another decomposition reaction, which means anything I change on the reactant side on the left is going to affect everything on the left. So I'm going to have to try to come up with some numbers that work for all of the elements at the same time, and that's going to be hard. So the first thing I would probably do is try doubling the left-hand side. If I do that, I'm going to have 6 carbons, 10 hydrogens, 6 nitrogens, and 18 oxygens. But the problem is then so if I just to look at that, 10, 6, and 18. The problem here is the only way now to balance the hydrogen would be to put a 5 in front of the water, which would give me 10 hydrogen, but it would give me a total of 2, 4 oxygens in the other compounds, and then 5, which would be 9. And so with an odd number of water molecules, I can't ever have an even number of oxygen atoms. So that's not going to work. So what I would try next is to go back and double the numbers. So I'm going to make this a 4, and I'm going to make this a 10, and it's going to be hard to see because these are so close together. But now I'm going to have 12 carbons, 20 hydrogens, I'm going to have 12 nitrogens, and I'm going to have 36 oxygens. Now this is where the numbers start to get bigger, but the coefficients for the most part are still relatively small. Some of them are going to be big, like in this case I need 12 CO2s. It's hard to fit in there. That gives me the 12 carbons I need. I need 6 in front of the nitrogen. And when I put the 10 in front of the hydrogen, the water, it gives me 20 hydrogens. Now I got to look at all the oxygen. So 12 times 2, that gives me 24 in the carbon dioxide. 10 times 1 is 10, so now I'm up to 34. And plus 2 on the end gives me a total of 36 oxygens. So that's balanced. It's 4, 12, 10, 6, and 1 for the coefficients. Okay, find the empirical formula of a compound that contains nitrogen, hydrogen, carbon, and oxygen. And then determine the molecular formula if the molar mass is 60 grams per mole. So to find the empirical formula, we're going to take the 1.21 grams of nitrogen divided by 14, that's the mass of nitrogen, which gives me 0.080. I'm going to do 0.161 grams of hydrogen divided by 1, 0.161 grams, 0.480 carbon divided by 12 is 0.040, and then for oxygen it's 0.640 divided by 16, which is 0.040. So I've converted all the grams to moles, and now if I look at the numbers I've got here, the smallest out of all these numbers is actually the same for carbon and oxygen. It's the 0.040. So I would divide all of these answers by 0.040. 0.040 divided by 0.040 and 0.040. So for the nitrogen, I get a ratio of 2. That was this one over here. For the hydrogen, I get a ratio of 4. For the carbon and the oxygen, I get ratios of 1 and 1. So that would mean that the empirical formula would be N2H4CO. So that's the empirical formula. So that's part A. The molecular formula we find by taking the molecular mass, which is the 60.1. We divide it by the mass of the empirical formula. So this would be N, 14 times 2 is 28, plus 4 for the hydrogen, plus 12 for the carbon, plus 16 for the oxygen. That actually adds up to 60, which means that the molecular formula is the same as the empirical formula, N2H4CO. It's actually not written that way in the actual formula, but this would be the answer I would expect from you for N2H4CO. Okay, so if we react 1.5 grams of barium oxide with 0.68 grams of hydrochloric acid, how many grams of barium chloride would be produced? Barium chloride. So, first thing we need to do is figure out which is going to be the limiting reactant. And the sort of simplest way to do that is to start the stoichiometry with each of the two reactants, and then when I get to the moles of product, at that point, whichever number is smaller is going to be the one I'm going to continue with, because that's going to be the limiting reactant. So let's start. We've got 1.50 grams of barium oxide. The mass of barium oxide is 169.3, which means there are 0.00886 moles of barium oxide times the mole ratio. In the equation, both barium oxide and barium chloride have coefficients of 1. So that means I'm going to have the same number of moles of barium chloride, 0.00886 moles. Now let's look at the hydrochloric acid, 0.68 grams, and the mass is 36.5, which means there are 0.0186 moles. And you might think at this point, well, obviously that's more than the other one, but you have to take into account the mole ratio. It might be the limiting reactant, or the excess reactant rather, but you have to take into account the coefficients to be sure. So the coefficient here is 2 for the hydrochloric acid and 1 again for the barium chloride, which means that the number of moles of barium chloride that we would get here would be 0.0093. Okay, so the barium oxide is the limiting reactant, because that's the one that so far has given us the smaller number of moles. To find the actual amount of product, we multiply the 0.0086 times the mass of barium chloride, which would be 208.3 grams. And when we do that out, we get an answer of 1.85 grams. So that's the answer to part 1. The answer to part 2, or B, is how many grams of excess reagent or reactant, same term, would be left over. Well, the excess reactant is the hydrochloric acid, so we got to figure out how much of that gets used. To figure that out, we need to figure out how much hydrochloric acid gets used if 1.5 grams of barium oxide get used. So we already did this step up above, but I'm just putting it down here just to show you where the numbers are coming from. We have 0.00886 moles of barium oxide. The mole ratio of hydrochloric acid to barium oxide is 2 to 1. So we're going to have 0.0177 moles of hydrochloric acid used times the molar mass of hydrochloric acid is 0.646 grams. Now that's not the answer to the question. The question was how much is left. What we've just determined is how much got used. 0.646 grams is the amount of hydrochloric acid that's consumed by this reaction before the barium oxide runs out. At that point, if you started with 0.68 grams and you used 0.646 grams, then you have 0.034 grams remaining. That's the answer to the second part of the question. All right, so the rest of these questions have to do with how much magnesium oxide is produced, how much should be produced, and then a percent yield. Okay, so there's several parts to this question. I want to just say right now that when I redid these numbers, I didn't check them before I put them into the test, and as it turns out, the percent yield that you will get when you do this with the numbers that I put in here, you're actually going to get more than 100% yield, which is actually not possible, and the one on the test won't be like that. But I just was changing numbers around, picking different numbers, and ended up choosing a set of numbers that gave a greater than 100% yield. So that was just sort of a unfortunate fluke. That won't happen on the test, and that shouldn't happen anytime you do this in the lab. That would be a sign that something has gone wrong. So, first question, balanced equation for the reaction between magnesium and oxygen to form magnesium oxide. Well, magnesium plus oxygen produces magnesium oxide. The only thing that's not balanced here is the oxygen. And I need 2 magnesium oxides to give me 2 oxygens, which means I also need 2 magnesiums. So there you go. There's the balanced equation. 2 magnesium plus oxygen, O2, produces 2 magnesium oxides. So what is the theoretical yield based on the mass of magnesium that is present? Well, the mass of magnesium is found by subtracting the mass of the crucible with the cover from the mass of the crucible cover and magnesium together. So I take the 108.46 and I subtract the 105.26, and I get an amount of 3.20 grams of magnesium. So that's just the start. Now the question is, how much magnesium oxide would I get theoretically if I start with 3.2 grams of magnesium? So now we have to go through the stoichiometry. And remember that it's 2 mg plus O2 produces 2 mg. So I'm going to start here. This is my amount given, 3.20 grams. The mass of magnesium is 24.3 grams per mole. So that means in this reaction I have 0.132 moles of magnesium. The ratio of magnesium to magnesium oxide is 2 to 2, or 1 to 1, which means I have 0.132 moles of magnesium oxide. The mass of magnesium oxide is 40.3 grams. 40.3 grams times 0.132 is 5.32 grams. So that is the theoretical maximum amount I could get if I start with 3.2 grams of magnesium. Okay, so calculate the volume of oxygen at STP, which stands for standard temperature and pressure, which just means that at standard temperature and pressure, 1 mole of oxygen is equal to 22.4 liters. We can't use that 22.4 if the conditions are not standard temperature and pressure. That's the only reason that's in there. All right, so this is another stoichiometry problem, except instead of converting to grams of oxygen at the end, I'm converting to volume, liters. So I'm going to start with the 0.132 moles of magnesium that we started with, because we established that in the last problem. I multiply that by the mole ratio. Remember, it's magnesium, 2 magnesium plus O2, 2 magnesium oxide. So the ratio of oxygen to magnesium is 1 to 2, which means I'm going to have 0.066 moles of oxygen. And if 1 mole of oxygen is 22.4 liters, then 0.066 times 22.4 gives me 1.49 liters. So that's the volume of oxygen that would be required to react completely with 0.132 moles of magnesium, which is what we said we have in this reaction. Now, we have to figure out how much oxygen was actually used in the reaction. So to do this, we're assuming that we started with magnesium in the crucible, we ended with magnesium oxide in the crucible, so the only difference in mass should be the amount of oxygen used. So that's the first thing we need to look at. How much oxygen was added to the substance that's in the crucible? Well, according to these numbers, which again are flawed because I kind of made them up and didn't check carefully enough to make sure that this would all make sense, but we can still do the math just to show you what you would do. 112.208 minus 108.46 is 3.82 grams. So according to these numbers, the amount of oxygen that was added to the substance in the crucible is 3.82 grams. 3.82 grams divided by the mass of oxygen, O2, is 32, means that we reacted 0.119 moles of oxygen. So that's the answer to this part of the question, or this question in this set. Okay, so that's how many moles of oxygen were actually combined, and how many moles of magnesium oxide were actually produced. Well, if we have 0.119 moles of oxygen used, which is what we said in the last question, the answer from the last question, and the ratio of magnesium oxide to oxygen is 2 to 1. For every mole of oxygen burned, we should get 2 moles of magnesium oxide. Well, then we would have 0.238 moles of magnesium oxide. Okay, so that's, again, how much we should have gotten, actually based on the amount of oxygen that was used. Why are we going through this when we already know how many moles of magnesium we used? Because when we do this, and as we saw in the lab, when we actually did this in the lab, all of the magnesium isn't necessarily burned in the combustion part of this. So just saying we started with so much magnesium, we should get this much magnesium oxide, isn't the most accurate way to do it. The most accurate way to do it is with the actual amount of oxygen that was consumed and added to the substance, because that doesn't account for, doesn't include any unconsumed magnesium, which might still be in the crucible changing the mass. So that's why we're doing it this way. So the last part here is calculate the percent yield, and this is where it gets really out of whack with what it should be, because the numbers are a little off here. Calculate the percent yield based on your answer number 5. Well, your answer number 5 said that your actual yield, or your actual yield was 0.238 moles, which means your actual yield here was 9.59 grams. And in the theoretical yield, we calculated that the theoretical yield was 5.32 grams. Which means that if you do that out, you get a percent yield of 180%, which is not possible. Okay, so we just have to take that into account. So again, that wouldn't ever actually happen in the lab, and the question on the test will not work out that way. But if you did get the 180%, even though I told you in class you could never get that, that's the answer you should have gotten based on the numbers that I gave you for this problem, which was a mistake to give you the numbers here without having gone through the entire problem, so it turned out at more than 100%. So there you go. So that's it. That's what the test is going to look like. These are the types of questions you're going to see: balancing, identifying reactions, molar mass, molecular mass, empirical formulas, molecular formulas, and the stoichiometry problems, including limiting reactant and percent yield. So we'll see you on Monday.